The SAT is not just going to do linear equations and quadratic equations. It occasionally does cubics, I guess, so it does some polynomials is the main thing you're going to see. But you will see other forms of equations, and in particular, exponential growth and exponential decay. So I want to introduce that topic, give you some theory on it, give you some things to look for. In the next video, we're going to see some word problems with exponential decay, things like interest rates and all that good stuff. But first, I just want to introduce the idea and show you how it compares to linear and how it compares to, kind of how it compares to quadratic, mostly how it compares to linear. So the general form of an exponential is this: y equals b to the x, where b is a constant, not a variable. So it could be a number like, well, it is a number like 6 or 2 or -1/2 or whatever. And then x is your variable as normal. So if you wanted to know the shape of this, what I might recommend is let's do an xy table, right? You could graph it in your graphing calculator, but let's do an xy table so we can see how this thing behaves. So here's our x and here's our y. Let's begin with 0. So 2 to the 0 is always 1. How about x is 1? Well, that's going to be 2. And x is 2. That would make it 4. X is 3. That would be 8. X is 4. That would be 16. And let's go do some negatives. X is -1. Remember, 2 to the -1. It means you do 1 over 2 to the 1. It's the reciprocal. So this becomes 1/2. -2 is 1/4. And okay, so let's see what we've got. We've got 0, 1, 1, 2, 2, 4, 3, 8, 4, 16, and then we've got -1/2, -2 1/4. So we get a shape that looks something like this. So we can see as x gets bigger, this thing just absolutely explodes, and that's because the exponent just makes it get bigger and bigger and bigger. So on the one hand, if we just take a second to compare it to parabolas, it almost looks like on the right, it's like half of a parabola, but as you can see on the left, it actually approaches this x-axis, what's called asymptotically. In other words, it approaches it, but never actually touches it. And that's because as you make that exponent more and more negative, you turn this into a fraction with a bigger and bigger denominator. So it's getting closer and closer to 0, but it's not quite reaching it. But this is the general shape you're going to see with exponential growth. It's going to start off slowly, but then pick off steam and absolutely just explode as x gets bigger and bigger and bigger. And that's the point of exponential growth. Something that's exponential increases the rate at which it grows. So if you compare this to a line, for example, let's like draw this line. The line is increasing, just like the exponential growth function's increasing, but it's increasing at a constant rate, right? We can find a constant increase in this function for a constant increase or decrease in the x value, and we call that the slope, right? The slope just is that constant rate of change, that constant increase. But in the case of this exponential, there is no constant rate of increase. It's just absolutely accelerating, getting faster, getting bigger and bigger and bigger at a faster and faster and faster rate. So there is no constant slope here. And we're going to use this on problems where we want to identify whether something is linear growth or exponential growth or whatever. Let's take a look at another form. This time we have 4 times 1/2 to the x. And again, just to get the form of this, we're going to make an xy table. So if x is 0, 1/2 to the 0 is 1, and 4 times 1 is 4. If x is 1, 1/2 to the 1 is 1/2 times 4 is 2. If x is 2, we're going to get 1/4 times 4, which is 1. If x is 3, we get 1/8 times 4, which is a half. If x is 4, we get 1/16 times 4, which is a quarter. We'll do some negatives. So 1/2 to the -1, a little bit confusing. 1/2 to the -1 is the same thing as 1 over 1/2 to the 1, which is the same thing as 2. You also could actually just 1/2 to the -1 is the same thing as 2 to the 1. Just flip the fraction and make it positive. But we'll talk more about exponents some other time. To go more detail about fractional and other exponents. Anyway, so we are, I think this is good enough. Maybe we'll do -2. And if we do -2, we'll get 4, because 1/2 to the -2 is the same thing as 2 squared, or 1 over 1/2 squared, and that leads us to 4. So let's sketch this out. Here's 0, 4, 1, 2, 2, 1, 3 1/2, 4 1/4, -1. Wait a minute, this should be, oh, I forgot to multiply this. This is 2, right? 1/2 to the -1 is 2, but then we got to multiply it by 4. So this becomes 8. Sorry about that. This is 8. Got to multiply by that 4. And then -2, plug that in for x. 1/2 to the -2 is, as we said, 4. And 4 times 4 is 16. Okay, so 1, 2, 3, 4. So here would be 1, -1, 8. And -2, 16 would be like that. So long story short, we get a curve that looks something like this. And notice it's actually kind of the opposite of this curve, this exponential growth curve, right? This gets bigger as x gets bigger and gets smaller as x gets smaller. This one gets bigger as x gets smaller and it gets smaller as x gets bigger. So really it's just the flip of this curve over the y-axis, essentially. But anyway, so what can we say about this? This is called exponential decay. Whereas this one is exponential growth. And it kind of makes sense. If you're looking at it from the perspective of x increasing, this function is growing, this function is decaying. So you want to be able, again, to recognize both. See that, again, if we drew a line decreasing, the same lessons that we learned about the comparison of this to a linear function are true, right? This is decreasing at a faster and faster and faster rate, whereas this is decreasing at a constant rate. And you can maybe identify that in tables or in other data, and we'll see that in a little bit. But what you want to know, you don't really need to know these equations specifically, like how to get the graphs. You're not going to really have to sketch out a graph on the SAT. But you do want to know the general form and the general behavior of exponential growth and exponential decay, because it helps you with questions like this. The half-life of a radioactive isotope is the amount of time it takes for 1/2 of the mass of the isotope to decay. TC99M, a radioactive isotope used in medical diagnostics, has a half-life of 6 hours. For example, if 100 grams of TC99M enter the body, after 6 hours 50 grams remain, and after another 6 hours 25 grams remain, and so on. Which of the following charts best depicts the relationship between time t and mass m of the TC99M introduced into the body? So a lot of words here, but the key is this portion here, this half-life discussion. This thing is decreasing over time. So we know right away, I mean, they're all decreasing, but we could probably get rid of A because A is slightly increasing, decreasing, and then increasing again. It should be constantly, well, not constantly decreasing, but it should be decreasing as time moves forward. So in fact, probably D can go because this is slightly increasing and then decreasing. So really it's going to come down to, is this a linear decay? Or choice B, is it an exponential decay? And you might guess, given the topic of this lecture, that it's exponential, but let's explain why. So what I might recommend is, again, kind of sketching out what's being shown here. So here's time, here's mass, here's 100, and the half-life says after 6 hours, half of it decays. So it goes from 100 to 50, and then another 6 hours pass, and it goes from 50 to 25, and then another 6 hours would pass, and it would go from 25 to 12.5. So we can kind of sketch that out. Here's 6 hours, here's another 6 hours, so here's 50. Here's another 6 hours, so here's 25. Right? So each 6 hours, we're going to decay in half. And what shape do we get here? We actually get exponential decay, and that's why it's choice B. So being able to recognize, sometimes you get a word problem and you have to see that it's decaying in a certain way or growing in a certain way. What you can often do is sketch out a little graph, sketch out a relationship, see how these are changing over time. If you note the first 6 hours, there's a decrease of 50. The second 6 hours, there's a decrease of 25, right? So the decrease over those 6 hours is not constant. If it were constant, then it would be linear, right? If it decreased every 6 hours by 25 grams, that's a constant linear decrease, and you would get something like choice C. But once you sketch it out, you see that this is very clearly an exponential decay. Okay. Actually, this probably should have been like this, but anyway, doesn't matter. Number of new cases of disease X by week. So we have a table here. An epidemiologist is studying the spread of disease X in a small town in Canada. In Canada. If the number of new cases of disease X is experiencing exponential growth, is it if the number of new cases of disease X is experiencing exponential growth, it is the responsibility of the team to call the outbreak an epidemic. Should the epidemiologist call this outbreak an epidemic? So basically, we want to know, does this table show exponential growth, or does it show something else? So what we want to see, again, like we talked about here, is what is the change as we go from week to week, right? As we increase 1 week each time, what is the change in the number of new cases, and what does that show us about the rate of change of this particular situation? So notice in the first week, it increases by 50. The second week, it increases by 75. The third week, it's increasing by, looks like 82 something. Next week, it's increasing by, what is this, like 123, something like that. Next week, it's increasing by 250. No, this would be 120, 112. This would be, looks like 253. Point is, this thing is increasing at an exponential rate. It's increasing at a rate that's increasing, right? This is not a constant change. If we saw 100, 150, 200, 250, 300, that would be growth, but it would be linear growth. What you want to see in the case of exponential growth is that increase is itself increasing. So we're increasing by 50, and then by 75, and then by 82. I think this was supposed to be 659. That would make a bit more sense. In any event, 225, 337, 506. So it's increasing at an increasing rate. Therefore, it looks to be exponential growth. So we can get rid of the nose. It is not increasing at a linear rate, and it is experiencing exponential growth. Yes, because the number of new cases increasing at a constant rate. No. Yes, because the number of new cases experiencing exponential growth. Yeah, that's the whole point. It is not increasing at a constant rate, right? It's increasing at a rate that is itself increasing. So we go with choice B. Which of the following situations would most likely lead to exponential growth in population? So let's see. Every year, the population of the United States increases by 10,000. So notice that would be growth, but that increase every year is the same. It's plus 10,000, plus 10,000, plus 10,000, right? That's a constant change. That's not an increasing change. So we can get rid of choice A. Every year, the population increases by 10,000 more than it did the year before. So you might think this could be exponential, right? It increases by 10,000, and then by 20,000, and then by 30,000, but it's not quite exponential because basically what you need is not just a flat increase, as you'll see in the next video. You need a percentage increase. You need to increase by 3%, as we'll see in choice C, or 5% or 20% or whatever. That gives you an exponential increase. So even though this is increasing at a constant rate, it's increasing its rate at a constant rate, if that makes any sense. Point is, as we'll see in another example question of this on the real test, this is not going to be exponential because it's got to increase by a certain percentage of itself. That's where you get exponential growth. So indeed, C looks good because that is an increase of 3% of the last year's population. This is a 3%, but it's 3% of the population of Canada. We have no idea what's going on with the population of Canada, so we have no idea whether or not this thing's actually growing exponential. So the point of this question is to show you that exponential growth, another way to think about it is when you have something increasing by a certain percent of itself every year. Because why this is exponential is the next year this grows, it grows by 3%, but it grows by 3% of its new, bigger population. So that rate of change is going to increase rapidly as this thing goes on because it's increasing by bigger and bigger and bigger amounts every year, not just a flat 10,000, because eventually that flat 10,000 is not really going to mean anything. But that 3% is going to get bigger and bigger and bigger as the number itself gets bigger, which is why we get something exponential for choice C.